Welcome to today's lecture on mathematical structures. We are going to look at special structures which are very significant in mathematics and not only in mathematics. These are called topological spaces. So there are two ways, or there are many ways, but among them, two ways how one could start this topic. One would be to start with a very concrete example and try to build up the general notion from that concrete example. And the other would be to give the general definition and then explore the examples. This time, unlike the last lecture where we talked about groups, I'm going to take the second approach, where first I'm going to formulate the general definition, and then we're going to look at examples. So the fundamental notion here is that of a topology on a set. The intuition here is that we want to equip a set with some information that makes this set behave like a space, like a real-life space. Now, there are many ways of specifying this spatial structure to a set, and all of them are called topologies, but then an adjective determines which way we are using. What we're going to define here is called an open topology. Open set topology. And the other ways I mentioned turn out to be equivalent to this one, but there are so many equivalent versions of it that we will definitely not be able to talk about most of them in today's lecture. So an open set topology usually it's denoted by tau on a set X is an element of the double power set of the set X, such that certain conditions hold. In fact, let me rephrase this a little bit. I want to think of it not as an element of it, but as a subset of single power set of X, where, let me remind you that the power set of X stands for the set of all possible subsets of the set X. Now, we already know what is a lattice. That was explained in another lecture. And once we understand the notion of a lattice, it becomes more convenient to state the axioms of topology. But I'm first going to state the axioms in a less convenient way, and then we're going to establish the link with a more convenient way. So there will be, in the less convenient way, there will be three axioms. The first one will say that both the set X and the empty set, they're both elements of tau. The second axiom says that if A and B are elements of tau, then A intersected with B is also an element of tau. And the third axiom says that if I have some subset of tau, let's say S, then the union of this set S will also be an element of tau. Okay, let's recall some of the definitions here. So what is A intersected with B? Well, it's the set of all entities which are elements of both A and B. So I think that's something that you probably know quite well. Now, what do I mean by this unary operation of union? So what I mean by this is the same thing as it would have been written this way: union of all, let me call these things C's, where C is an element of S. In other words, it's the set of all those entities for which there exists some C in S, such that that entity is an element of C. So, for example, if the set S consists of 3 elements, so these are 3 different C's, C1, C2, C3, then according to this definition, you see all the elements of each of these C's must be contained in the union. So if I expand each C into sets of their elements, then everything that will ever fall in here is what constitutes union S. So in other words, the union S is the set that I've enclosed in this green region, the one that consists of the green points. So this is going to be union of S. So start with S, breaking down into elements, break each element further down into elements, and then take all these elements and form a new set from that. And that new set is the union of S. A link with something you would have seen a lot, union of 2 things, that can be defined as the union of the set where these 2 things are the only elements. Now, the reason why we want these unions of not just 2 things, but of any set S, is because we want to allow infinite unions as well as finite ones, which are, of course, included in here because of this equality. Okay, so these are the 3 axioms that define a topology, more precisely an open set topology on a set X. Now, where do these axioms come from? The key example is the 3-dimensional space that we think we live in. In this space, okay, let me call this motivating example. It turns out that some portion of what makes up the space can be specified by a very specific topology on R cube, which is the following. So we will consider a tau, a specific tau. Remember, tau needs to be a subset of the power set. So we will consider a specific tau, which consists of the following sets. So the elements of tau are defined by the following property. I now want to actually use a different letter here for the reasons that will become apparent later on. So in the 3-dimensional space in R cube, when will a subset, in other words, an individual element of the power set of that set, be considered to be inside tau? Let's draw some subset there. So let's say some kind of three-dimensional shape like this. And the requirement we're going to make on this thing will depend on the elements of that set. And in fact, we will say something about every element of that set. So if I pick an arbitrary element of the set, so for any small a in big A, I must be able to find an open sphere centered at that element and enclosed entirely in the set A. And of course, an open sphere centered at an element is uniquely determined by the radius of the sphere. So I will say for any A and for any R, a real number, a positive real number. So R is an element of R plus. So this would be the set of all those real numbers that are bigger than 0, strictly bigger than 0. The sphere S centered at A and having radius 1. What does that mean? So all the elements B of R cube, such that the distance between A and B is strictly less than R. This thing here represents the distance between A and B, which we can measure, right? Either using a ruler or using a beautiful formula expressed in terms of coordinates of A and B and the Pythagorean theorem. Okay, so for every A and R, this thing must be contained in A, which is to say that it must be a subset of A. So we can now write down exactly what tau is. Tau is the set of all those subsets of R cube, such that I'm going to use some symbols for mathematical logic, such that for every A in A, and for every R in R plus, my apologies, I don't want to say for every R, I want to say for some R. So I don't want, of course, if I require that every single sphere centered at my point is contained in the set A, I can make my sphere to be as big as I like, and eventually A will have to be the entire space, right? So what I want to say here is for any A and some R, so that the R must exist, and it must exist for each A. So let me put it more elegantly here. For any A there exists R such that this sphere is entirely contained in A. So I have to use here then the existential quantifier. So for every A, the R exists such that SAR is a subset of A. So this is the definition of tau, which we will confirm that satisfies the three axioms that we wrote down there, up there. Okay, before we look at those axioms, right? Let's give some examples of what kind of subsets of R cube are actually elements of tau. So what about the spheres in general? Will they always be inside tau? So some examples of elements of tau. Imagine I take a sphere centered at the origin of the coordinate axis and whose radius is 5. Will this A equal to such a thing? Will it satisfy the condition we wrote there? And let me remind you what these symbols mean here. So this means for every, and this symbol means there exists. And it's important the order in which they appear, because it says that once I choose an A, for that A, the R must exist. So this R will most likely depend on A. Okay, so imagine now we take a sphere. So this is my A. And I take its center. The center in this case we agreed to be 0, the origin of the coordinate axis. So it's actually the vector 0, but I'm not going to use the vector notation here. And now I need to check that this condition holds, right? So I begin by picking a random element A in here. And now I need to find a radius R, so that a new sphere, the sphere that's centered at A and has radius R, will be entirely contained in the set A. Do you think I will be able to do that? Will I be able to find such R? What do you think?
Just to be clear, Prof, when you say sphere, do you mean the two-dimensional surface together with the interior, or just the two-dimensional surface?
That's a very good question. The way I defined it here, you see, I'm requiring the distance to be strictly less than a certain radius.
Oh yes, okay. We include the
so the
interior.
so the right. The surface is not included. So will I be able to find such R?
Yes.
How? What do you think we should make it equal to? So I'm looking for a radius, so that if I measure that radius off from A and I make a new sphere, right? That this is entirely contained in the set A, in the bigger sphere. So how do I find the R, so that if I measure R here, if this length is R, that ensures that this thing is contained wholly inside. I mean, I know that small a is contained inside capital A. I now want a sphere surrounding small a also to be contained inside capital A. So this small a is somewhere inside the sphere. It cannot be on the surface, as we just said. the radius being 5, the sphere is defined as all the points whose distance from 0 is strictly less than 5. So it can't be on the surface of this. A cannot be on the surface of the big sphere. Any ideas how to compute R?
We can take 5 minus R.
We could take 5 minus R, but we want to find R.
Oh, yes. Okay, no.
What we do know is that this length here, from 0 reaching to the end of the sphere, is 5. That we do know. Maybe it will be to give you a bit of a hint for me to draw that same line right here, aligned with R. So that length, the big one here, is 5. We want to fit in an R there.
We can take the 5 minus the distance from 0 to A.
That looks like a good idea, yes. So we measure distance from 0 to A, and we subtract that from 5. And then, of course, I could now prove that this thing over here, with this R, so 5 minus distance 0A, is a subset of A. And how would I prove that? Well, I will pick an arbitrary element. So I want to prove this. So I'll pick an arbitrary element. Let's call it X. In such a sphere. Let me just call it R for now. What do I know about that element? Well, I know that the distance between A and X is less than R, which is 5 minus distance between 0 and A. What I want to prove is that X lies inside the big sphere. And to prove that, I would have to prove that distance between 0 and X is less than R. So this is what we're wondering, whether distance between 0 and X is less than R or not. And of course, the fact that point A lies in the big sphere means that we do know that distance between 0 and A is less than 5, right? So now combining this information together with this, will I be able to deduce this?
Is it possible to use the triangle inequality?
That's a good idea, yes. So intuitively, the furthest point inside the sphere we could get away from 0 would be this edge here, right? And because of the way we chose R, because R was the entire length minus that length, so this point must be within the R distance. And indeed, the triangular inequality is what we want to use here. This is when the triangular inequality would turn into an equality. So the distance between 0 and X will be less or equal to the distance between 0 and A plus the distance between A and X by the triangular inequality. If you haven't heard what a triangular inequality is, it's a very basic fact about distances that you surely know from real life, that if you measure distance between 2 points, so here the 2 points are, let's call them U, W, and V. So if you want to measure distance between U and W, and you've been able to measure distance from U to some V, you've done that, and you also measured distance from V to W, then no matter where V lies, the sum of these distances will always be bigger or equal to the direct measurement of distance between U and W. You can see also from the shape of the triangle that this plus that will be more than that. That's why it's called a triangular inequality. So we can then compute the right-hand side here, right? So the distance between 0 and A is less than 5, so I can say this is strictly less than 5 plus the other one, which is also strictly less than that, right? So I could just write it this way. Wait, maybe I don't want to do that yet. I think I want to keep my D0A for now and just replace DAX with the thing that is strictly less than, so that D0A and D0A cancel with each other. And I get that this is less than 5, which is exactly what I wanted to prove. Yes, that's what I wanted to prove. I don't know why I wrote that I wanted to prove it's less than R. We didn't want to prove that. We knew that it's less than R because X was inside that sphere, and we wanted to prove that X is also the bigger sphere. So I apologize for that. I should have written here 5, not R. Okay. So you see, for the big sphere, we've managed to confirm that an arbitrarily chosen element in it can have a smaller sphere which lies inside the big sphere. And in general, the subsets of R cubed, which will have this property that makes them be an element of the topology, will be those which kind of are subsets that do not contain the surface, because as soon as you remove the surface from something, so let's say we take some wobbly shape like this, right? And so it's a 3D shape. We're looking at kind of upside down. So I'll draw these lines to help us picture that it's actually a 3-dimensional thing. We're looking at this wobbly shape, and you kind of peel off the entire surface from that. Because you peeled off the surface, then anything that you will, any point you will pick inside, right? Any point that will be inside the surface, so not on the surface, but within your shape, will always have some very close distance to the surface, because it's not on the surface, so there must be some distance from it to the surface. So the shortest distance you'll try to figure to the surface here, something like that. And then, so this point is inside, and then you take that shortest distance, and then you take a sphere whose radius is smaller than that, and then you manage to contain the entire small sphere containing your starting point inside your big set. So as soon as your set doesn't have surface, in intuitive terms, I mean, what I'm saying now is not very precise, of course. It's just for us to picture a large variety of examples. As soon as it doesn't have surface, it's contained inside tau. So these are the kinds of things which we put in the set tau. Now, in general, these things, the elements of tau, in other words, these examples of sets we've been considering here, they're called open sets. And I forgot to mention that here, so let me edit this here. In an open set topology, elements of tau are called open sets. So this notion is dependent on the topology you choose. It might be that for every set X, there are different ways of choosing topology. Even for R cube, you see, even for R cube, there might be different ways of choosing topology. But here, in this specific example we're talking about now, we are fixing one specific way of choosing topology, and that's where open sets are three-dimensional bodies without surface. So let's write this down. In this example, we can think of open sets as subsets of R cube that are surface free. And this notion of surface free is very imprecise notion at this stage, at least. It becomes possible later on to formally introduce what a surface is, but for now it's just used as an illustration of the idea of how to think of these things. Now, why would we care about these special subsets of R? Those subsets, those wobbly shapes like these, which do not contain the surface, because in topology, in the subject of topology, it's a field of mathematics which primarily, but not only, studies topological spaces. We would like to model the realized space by just one simple aspect of the realized space, and that is the aspect of continuity. So how does this idea of considering these open sets capture a continuity? You can think of, let's go back to this set A, the big sphere without the surface. You can think of this as an area inside which you could continuously come closer and closer to the edge, never actually arriving to the edge. And whatever is on the edge, that you can think of that being continuously approached from inside the sphere. Now, it turns out that just by knowing what the open sets are, we can actually, in fact, already with this structure of open sets that intuitively I tried to explain to you why that captures continuity, we could actually now use them to define continuity in terms of that. We can start by defining what is the limit of a sequence just using open sets. So let's do that. Open sets model continuity in a real life space. Consider a sequence of points. So it's an infinite sequence. So let this be an infinite sequence of points in our cube that approach, well, actually, let me phrase it the following way. Then the limit of this sequence will be equal to some point x, if and only if This is the symbol for if and only if. For every open set containing X, there exists a natural number n such that so let's call this open set A, such that for every n bigger than n, for every small n bigger than, let me actually use a better notation here. There exists small n such that for every m bigger than small n, we have that this term, mth term of the sequence, is entirely in A. So what are we saying here? We've got a sequence of points, right? And of course, this on the left side, what we mean is the usual limit. If you don't know what a usual limit is in R-cube, then you can just recover at least intuition from this following picture. So you've got basically a sequence of terms, x1, x2, x3, x4, and they maybe they go in a spiral, maybe not, but eventually they come closer, and they continuously go closer and closer to some point x. Okay. And if they do that, if they come closer and closer to point x, then of course this will be true. Why? Because I will pick some. I want to prove that for every open set this happens, right? So I'll pick some open set. So this is my open set A. That surrounds X, right? Then by the definition of open set, that means that there is some sphere surrounding the same small x, but lying inside the big set A. And why is it that all the terms of the sequence will be inside big A? Because they will actually be inside the sphere. Why will they be inside the sphere? Because we said that these points come closer and closer to X, and by fixing a sphere, we fix some distance from X, right? And if they do come closer and closer to X, then after some point in the sequence, all the terms will be closer to X than the radius of that. But if they're closer than that radius, it means that they all fall inside that small sphere, right? So that's how we get that this implication holds. And the converse implication is also easy to see. If I have this property, right, then I could take as my A, I could take my A to be already a sphere. If all these points fall into that sphere after some point in the sequence, it of course means that they are a certain distance away, right? By an argument similar to what we discussed here. And if they're if this is true for every single sphere A, we could start taking A to be sphere with a smaller and smaller and smaller radius. In fact, we could be choosing the A's that are centered at X to have a precise match of being inside A and distance being less than a given number. And so that means that for every number, we will always be able to find a point in the sequence after which all the terms in the sequence are that close to X, because they must fall into the sphere whose radius is that number. and that means that they're that close to x. So I've kind of avoided in this discussion stating the precise definition of this in terms of distance, assuming that either you know that, and so you'll be able to understand the formal details of my argument, and if you don't know that, then I didn't want to confuse you with that. But nevertheless, let me, just for completeness sake, let me still state this definition. So without open sets, just with distances, this notion is defined in the following way. For every epsilon bigger than 0, epsilon is a real number. For every epsilon bigger than 0, there exists a natural number n, such that for every m bigger than n, we have that this xm's, that the distance between x and xm is strictly less than epsilon. And so the way it should have been apparent from my informal discussion for the last 5 minutes, the way these are related to the way this condition gets equivalent to be equivalent to that condition is basically by the transition that we can replace an epsilon with a sphere centered at x and radius being epsilon. And then if that is the case, then distance of these two being less than epsilon is equivalent to xm being in that sphere. All right, so this is just one illustration of how open sets can capture idea of continuity. There are many other ways we can illustrate the same phenomenon. For example, we could now also define continuity of functions using just open sets and so on. But that we're going to do in the second hour. I'm going to now stop the recording because of load shedding. I'm going to stop this recording so that it saves, and then resume in a few minutes when the generator kicks in and my computer restarts. I realize I can also pause the recording. Let me actually rather do that, because I will not be kicked out from Zoom. So we are continuing now with what we were talking about, and we gave some intuition in terms of how open set topology could model continuity in terms of this specific example. But we still need to confirm that this specific example is an example. We need to check the 3 axioms. So let's look at each of them. The first axiom says that the empty set must be open, first of all. And that is true because you see the way we defined open sets here, they are those subsets of R cubed such that for every A in that subset, something happens. If capital A is empty set, right, then there is no way to pick any element from that set. So this whole statement will be true trivially, simply because there's nothing to pick here. It's a similar principle as false implies anything done. So empty set is open. The entire set R cubed is open. Also, that's quite obvious as well, because I mean, I'm back, and I regret for not being more patient. So right after we decided to resume the recording, I had my electricity off. So we were saying that we want to now check the axioms, and I started writing something out, and then I had electricity cut. I think we explained why the empty set is open in this specific example, as well as the entire set, which in this case is R cubed, why that is open. And now let's look at, so that would make the first axiom. And now let's look at, maybe it was cut right in the middle of my explanation of why the entire set is open. So I was saying there that if we take A to be the entire R cubed, eventually the requirement is that the certain open sphere is inside A. But if A is in the entire R cubed, then of course this requirement is fulfilled, because after all, this is defined as a subset of R cubed. You see, the sphere is a set of all B's in R cubed such that something holds. The second axiom says that the intersection must be there. So let's say that A and B are open. We want to confirm that their intersection is also open. So why would that be? Why would that be so? I pick an arbitrary, I mean, what we want to prove is that if I pick an arbitrary element in the intersection, then there will be an open sphere that's completely contained in the intersection, right? That's the definition of being open in this example. So let X be an element in the intersection. But we do know that for each of the for each A and B, we can find such open spheres. Then there exist R1 and R2, both real numbers being bigger than 0, such that S centered at X and radius R1 is a subset of A. So that's because A is open. And because B is open, the one with the R2 will be a subset of B. Let me just check something here. Yeah, I just wanted to check that we do require that R must be positive. We don't want to allow R to be 0, because the sphere with 0, of course, would be empty set, and that will always be a subset of any A. So everything would be open if I allowed that case. But now we have two spheres, one for each set A and B, and we want for the intersection. But of course, because both of them are centered at the same spot, we could take the smaller one, and the smaller one will then be in both. So we define a new radius to be the minimum of the two radii we have, R1 and R2. Then the sphere centered at X with radius R will be indeed in the intersection. So, because, of course, that's because R is less or equal to both R1 and also R2. Two spheres have the same center and smaller radius, and they will be contained entirely in the bigger one. So one will be contained in the bigger one. Okay, so that's checking that intersection of two open spheres is still open. Now, what about union of arbitrary amount of spheres? So suppose S is a set whose every element is an open set. And now we take an element X in the union, right? But if something is in the union, it means it's in one of them, right? One of the things of which we are taking the union. So then X will be in one of the A's, which is in S, for some open A. But because A is open, we can fit a ball inside A. So the sphere with center X and some radius R will be a subset of A for some R bigger than 0. But remember, the union is the union of all of the, I mean, brings together all the elements of all the elements of S, right? So every element of A is certainly inside that union, not just the X. But this is a set consisting of some elements of A, so all of the elements of this thing are going to be inside the union. But that means that we've now fitted the ball inside the union, which is exactly what we wanted to do. So this is how we can confirm the three axioms hold. If you have any questions, if you're not sure about some part of the argument, please do ask them. While you're deciding whether you have a question or not, I would like to show you why does the intersection of infinitely many open sets does not work. So we saw here that the union of open sets, infinitely many, even that can be infinitely many, right? Because we're not putting any restrictions on the size of S. The union of open sets is always open, but what about arbitrary intersections? What if we had infinitely many sets to intersect? Why wouldn't that be open? And this is why. I could take a sphere with, well, actually, maybe a simpler example would be just take a single point, right? And then take the set of all possible open spheres that surround that point, or maybe that are centered at that point. Okay, take all of them. What is going to be their intersection? You see, because eventually they get smaller and smaller and smaller, right? Only the orange point will be in their intersection, nothing else. So the intersection of these infinitely many open sets is just a single orange point. But a singleton set in R cube cannot be open. Why? Because if it was open, there must be an open ball that fits completely inside that singleton set. But all the open balls always have radius strictly bigger than 0. And so you cannot take a single point and fit in it an open ball, an open sphere, cannot fit in a singleton set, because an open sphere will always have more than one point in it. So that's why we don't have that arbitrary intersections of open sets are open, but we do have that arbitrary unions are open. That was quite an easy argument to prove that. So now that we've motivated the notion of open set topology, let me show you how simple becomes the definition of a continuous function between topological spaces. In a way, the whole purpose of defining a topological space is to define a continuous function between them. Because when we said that topology models continuity, continuity is expressed in terms of continuous functions, and so that's the best way of confirming that fact, to define continuous function and to see that the definition is actually simpler than some other approach, maybe with distances or maybe even more primitive approach. So first, let's define a topological space. A topological space, and we could have said here again open set topological space, but we're going to drop that prefix for now. A topological space is a pair consisting of a set X and an open set topology tau given two topological spaces. They could be the same space. When we say two in mathematics, we don't necessarily mean that strictly two. It could be two that are the same. Even two topological spaces, x tau and y sigma, a continuous function from the first space to the second space is a function f from set x to the set y, such that for every a in sigma, the inverse image of a under the function that belongs to tau. So what is the inverse image? That's simply all the elements of x such that f of x is an element of capital A. Now let's compare this with the definition of a continuous function, let's say from r cubed to r cubed. Or maybe maybe from r to r cubed, because then we can nicely demonstrate the intuition behind that. So if I have, let's say, the real line, right? And I'm considering a continuous function from the real line to the three-dimensional space, I could think of my real line as the set of timestamps. And then my function can be thought of as a particle moving in the space. So let's say I've got timestamp somewhere 0. This is the location of the particle. So the value of the function at 0 is the location of the particle at a given point in time, the point in time called 0. And then as we increment the values on the real line, for every value there, every t represents some time that has elapsed from the initial time, and then the particle is moving, so at that time the particle would be at a different spot. So and also before the time we started observing the particle was somewhere in the past as well. So eventually we get this kind of wiggly line that represents the trajectory of the particle, but as a function it is not just trajectory, but it also gives me the entire information of at which point in time where is the particle. So that gives me the motion of the particle. And in this context, the idea of continuity is that the particle cannot jump. So if it's somewhere here, immediately next point in time, but of course there is no next point in time because we can always consider small and small time, but it can't be that, let's say we've been measuring from day 0 to day 5 and the particle was here, and immediately after that, once an infinitesimally small time has elapsed after 5 days, the particle is already there, so it kind of jumped from one place to the other. So the particle was moving like this and then suddenly disappeared, and then it appeared at some other place and continued moving like that. We don't want that to happen. So we say that the movement is continuous when that doesn't happen, when the jumps do not, when the breakups do not happen in that line. the line doesn't break up, basically. So how can we define what this means? We can, it turns out we can, using the notion of distance, and this is something you might have already seen at the first year of your university studies. So the definition would go as follows. We would say that for every, so I wanted to describe what it means for the function from the real line to R cubed to be continuous. It's continuous when for every x in R, and for every epsilon bigger than 0, there exists delta bigger than 0. So this epsilon and delta, they are real numbers, such that for every real number a, if, let me write this as an implication. So for every a, the distance between x and a being less than delta implies that the distance between f of x and f of a is less than epsilon. And you see this entire paragraph here this whole thing here shrinks down to this when you approach continuity from based on open sets. You see how efficient this language is. And also the translation shouldn't be too difficult to spot. Every time we talk about epsilon, this is actually some open sphere with radius epsilon going on there, and the same for delta. We're not going to go into proving now that these two definitions are equivalent, but just to give you some hints as to why they're expectedly related to each other. This condition, for example, is requiring that the A lies inside delta radius distance, so basically an open sphere, but on the real line. So it will be an open interval centered at x, radius delta. And so you can see how these open things enter the story. And similarly here, this is basically saying that f of a is within epsilon range from f of x. In other words, it lies inside an open sphere whose radius is epsilon. But they don't have to be spheres. We can just forget about spheres and just work with abstract open sets, and the definition is still equivalent to the previous one. We did describe explicitly what are open sets in R cube for this example to work. What about open sets in R? Well, I did mention them briefly now, but let me make it more explicit. So in here, A is open. The definition is very similar to the R cube one, except that we replace open spheres with one-dimensional open spheres, which are basically open intervals. Is open when for every x in A, there exists, so I'm now writing this definition not in the language of open intervals, but in more explicit language, is open when for every x there exists delta bigger than 0. So that's my radius of my intended open sphere, the one-dimensional one. For every x that exists delta, such that for every a in R, whenever the distance between x and a is less than delta, and that just means that the absolute value of their difference is less than delta, that implies that a is in capital A. And you see, basically, this is how this becomes a more efficient language, but we're kind of encoding this kind of constructs, right? Which we do find here. We're kind of encoding this kind of constructs into a single notion of an open set. And so that kind of encoding is what's behind the scenes here. By having chosen this encoding in a careful way, we then manage to break down definitions like this into simple conditions like that. Okay. So coming back to the notion of a continuous function, so this is how it's defined, and one can then prove various interesting properties of continuous functions. For example, the fact that composite of two continuous functions is continuous. We're going to prove that here in this abstract language, which is much easier proof than if we had to prove it in this language. By the way, this language using distances is applicable to more abstract spaces than R and R cube, where there is a suitable notion of a distance. Such spaces are called metric spaces. So it's basically an abstract set equipped with a function that maps to every pair of points in the space some number. And then there are some axioms to be satisfied. One of them is triangular inequality. And we can actually begin with any metric space and turn it into a topological space by defining open sets the way we define them today. But we're not going to go in that direction for now. So now let's take two continuous functions and compose them and see that the composite is still continuous. Composite of two continuous functions is continuous. And once we prove this, after that, I'm going to show you the intuition behind that result. So what do we have? We have basically space x star, space y sigma, and space z rho, right? We've got two functions, f and g. Each of them are continuous. So let's write what this means. F being continuous means that for every a in sigma, the inverse image of a under f is in tau, right? And g being continuous means that for every b in rho, inverse image of b under g is in sigma. And now we want to prove that the composite is continuous. So the question is whether this implies or not that for every b in rho, inverse image under the composite of that b will be in tau. So what do you think? If we pick b in rho, what computation must we perform to get convinced that this inverse image will be in tau? How can we simplify this expression, maybe to reduce to something that will make use of these two facts? While you're thinking of an answer, let me make a drawing. Yeah. So we've got the three spaces, x, y, and z. And we've got here a b. That's a set b. And now what is inverse image of b under g? Well, that's just taking all the elements in y that map to b, right? So possibly something bigger. So we just pick everything that maps to b. So that's going to be my inverse image of b under g. And then if I have something in y, let's say a circle like the one I've drawn here, its inverse image under F will be all the things that map to that region under the function F. So it will be something maybe even bigger. So in this specific example, this will now be F minus 1 of G minus 1 of B. So when is an element there? It's there if its F is in here. And when is something in there? It's there when its G isn't there. Okay, now let's come back to this. Do you have an idea how to simplify this? Anyone?
Could we perhaps set that equal to the inverse of F composed with the inverse of G of capital B?
Yes, but we don't say composed anymore, rather applied. So we apply inverse of F to inverse of G applied to B, right? So why are these two sets equal? Well, we already explained what this set is on the picture. What about this one? What is this set? This is all possible things in X, in the set X, that map by the composite map to Z. But then the picture is exactly the same, right? So if I have something in X, when will it map to by the composite to Z? When it maps somewhere here, then that further maps to B, right? Sorry, did I say Z? I want to say B. So this thing maps there. So let's call it small x, maps there, small y and small z. So x maps to y and y maps to z such that z is in B. But if y maps to z being in B, it means y itself is in here. And so that makes x in there. So these two sets are actually equal to each other. Let's maybe write this out more carefully. This set is the set of those x's in X such that the composite mapping applied to X is in B. But the composition of functions is defined so that the composite map applied to an element is the same as G applied to F applied to that element. So that must be in B. But now it's a general fact that G of A will be in B if and only if A is in G inverse of B, right? What is G inverse of B? It's exactly those A's for which G of A is in B. So something is in the inverse of B under G exactly when G of A is in B. So this thing tells us that G of F of X is in B. That just means that F of X is one of those that by G is mapped inside B. So F of X is in G inverse of B. But now the same story applies now, but now with the F. So F of X being in some A is equivalent to X being in F minus 1 of A, right? So here we're told here that X maps inside this set. So all the things that map in that set must contain X. But that set, instead of all the X's that are contained there, is of course that set. In other words, this one. Right? So that's how we get that these two things are equal. If the argument on the picture wasn't clear enough. And after that, there's not much to do, because now that we have this thing being equal to that thing, we want this to be in tau, right? But we do know that, I mean, we started with B that was in rho, so we do know that G minus 1 of B is in sigma, yes? But when something is in sigma, its F minus 1 must be in tau. So here we have G minus 1 of B being in sigma because B was in rho. And because that is in sigma, its F minus 1 must be in tau. I hope that argument is clear. If not, please do ask. And the proof is finished. Well, in the beginning, I promised you a simple proof, and maybe this is not so simple, but only because we recalled some very, very basic facts about sets and functions. Okay, so what's the point of this theorem? There is another way we can think of continuity, namely the following. Take a cup. And think of this cup being made out of Tau. So you can do some deformations to the shape, but without breaking, without tearing the shape. You're not allowed to tear. You are allowed to squash things together, but you're not allowed to tear. Then it's not difficult to imagine that by adjusting the shape of it a little bit, you can get a donut-shaped object out of a cup. So this hole that was there is that opening of the donut. Basically, you see all of this, all the left side. So this part is already kind of similar to half of the donut, right? So this half. So this is similar to that. What about the entirety of that? Well, that's just making a dent in the donut, but not tearing it, just making a little dent so that the inside of the cup can be separated, and then just giving it a bit of a volume on the sides. Now, you can describe this as a topological space by the idea of open sets based on the idea of open balls. And then this transformation of changing the shape of the set can be seen as a continuous function. So I'm not allowed to tear, but I'm allowed to stick things together. So I get a continuous function from set x to set y. Now I repeat the process. I again carry out further deformation, but I do not tear anything. So what shall we make out of the donut? Maybe we can make a very long, wiggly piece of band. We are stretching things just as before, but we're not tearing anything. That mark there, somewhere here now. So the previous theorem is a very basic fact telling us that if I didn't introduce any tier in this step, and neither I introduced a tier at that step, then when I combine the two steps, I'm not going to get a tier. So it's a very fundamental principle about continuity. What is interesting about this specific example of continuous functions is that we actually have reverse in each case. It's actually possible to go back. If I make a donut out of the cup, I can reverse the process in the same way here. And so when we can go back, that has a special, that those kinds of continuous functions have a special name. A homeomorphism between topological spaces x, let's say x tau and y sigma, is a continuous function, actually a continuous bijection f from okay, let me make the definition a bit more rigorous. So it's a continuous function f from x tau to y sigma, such that f as a function from x to z, is x to y, is a bijection. And moreover, when every bijection we know has an inverse function, the inverse going back from y to x is also continuous. Is a continuous function from the space y sigma back to the space x tau. And this is exactly what's happening here, where each of these deformations, they are actually bijections. We are stretching and squeezing things, but we are never taking 2 points and squashing them to exactly the same point. But moreover, they're the kind of continuous bijections where the reverse process is also continuous. Now, in general, when two spaces are homomorphic to each other, which means that there is a homomorphism between them, a topologist would regard the spaces to be essentially the same. So for a topologist, a coffee cup and the donut are the same thing. And they are the same thing in the sense that their continuous structure is the same. So remember, topology cares and actually only cares about the structure of continuity. And that structure, donut and coffee cup share the same. But let me give you an example of a different pair of sets where they do not share the same such structure. So consider a figure 8. Maybe yeah, so consider a figure 8 like this, where my space is now the that line, that infinitely narrow line, no? And a circle. There is still a continuous function running this way. Why? I could take these two wings of this kind of butterfly type of shape, right, and stick them together. So kind of bring them together like this. So I would do something like that. So that's my figure 8. where now these two wings are coming closer to each other, and eventually they are stuck to the same spot. But I can't reverse the process. Well, first of all, this is not a bijection anymore. And secondly, I won't be able to intuitively kind of start with this space and even to build a continuous function from here to there, I would struggle. Let me see if I didn't lie to you. So maybe you can help me here. Do you think we will be able to find, so I've demonstrated how we can find a continuous function running this way, but will we be able to find a continuous function going backwards? So I'm asking this question, of course, at a very intuitive level. Will I be able to imagine, I mean, having this band and being allowed to stretch it or squeeze it, but not to tear it? Will you be able to turn this band into something like this? Of course, yes, right? We can do this. How? Just bring endpoints close like that, right? And eventually stick them. But the function will have to take 2 points to the same point. So it won't be an injective function. It won't be a bijection. So while we do have a continuous function going in both directions, right? We won't be able to find two continuous functions that are inverses of each other. And intuitive way of seeing why we won't be able to find that is that they have different continuity structures. For example, here, if I think of continuity structure in terms of motion of a particle, if I begin here, right, I could go this way, and then I could make cycles, or I could make cycles in reverse direction. But here, I can make those cycles in forward or reverse direction, but I can do more. I can also go this way and cycle like that, and this path would be would have a different continuity structure than the first one, because I won't be able to, like, for example, you won't be able to like do this and then continuously do less of the loop here, less, so eventually it just becomes a loop here, because of this big hole in the space. You won't be able to bring this loop and squash it down to a single point, which is something you can do here. Here, you only go around one hole in one or the other direction, and so on. So there is a lot of interaction between the spatial intuition of continuity and the actual formal mathematics that's implemented through the notion of a topological space. So I've kind of tried to show you both sides of the story here, but of course the things I was discussing at the level of these pictures, like the donut and the cup and this figure 8 and so on. This was not meant to be rigorous mathematics, right? It was obvious it wasn't rigorous mathematics, but the subject of topology can turn this into rigorous mathematics. And in this specific case, the rigor comes in to say, to actually prove, using results from topology, that these two spaces are not homeomorphic according to this definition. So there is no homeomorphism according to this definition. You can actually prove this mathematically. Yeah? But the intuition behind that theorem is that these two things have different continuity structure. And I hope I've managed to convey what the intuition is behind this idea of continuity structure. And then there are many interesting things one can do with topological spaces. We are coming to the end of this lecture, so I'm not going to go into those interesting things. I just wanted to come back to the remark I made right at the beginning of simpler presentation of these three axioms. If we consider, so I don't have time to elaborate on this too much, but if we consider this lattice, so you had a lecture on lattices and also on complete lattices, where you can take arbitrary joins or meets of subsets. So if we consider this lattice, this pose set basically of power set, it has arbitrary joins and meets, or suprema and infima, in other words. And saying that you've got a subset tau of the power set, which is closed under binary meets, along with the largest element of this pose set being in the subset, is just to say that this tau is closed under finite infima or finite meets. So this axiom, together with x being in tau, becomes closure under finite meets, where you recover x as an empty meet. So if you take empty set, its infimum is going to be the largest element of your pose set. Whereas the other condition, that empty set is there and tau is closed under arbitrary unions, becomes the statement that tau is closed under arbitrary suprema, not just finite, but arbitrary. So then the axioms of topology are basically that it's a subset of this lattice of the pose set, which is a lattice, but it's irrelevant. It's a lattice. Well, it's actually not irrelevant because we want to make use of arbitrary suprema and infima in the definition. So the condition becomes that something is a topology if inside this pose set it is closed under arbitrary joins and finite meets. Now, why couldn't I say the same thing just with intersections and unions instead of joins and meets? I mean, instead of meets and joins. I did say here that this is closed under arbitrary unions. So why not just saying that it's closed under arbitrary intersections here? The thing is that if we step out from the power set, if we just consider all possible sets, and I define intersection of, like I define union of S, I just define intersection of S. So what would be intersection of S? Intersection of S would be the set of those X's which belong to every single element of S, right? So for every S in S, or rather for every C in S, X belongs to C. And then I try to compute the intersection of the empty set. This will be all the X's such that for every C in the empty set, something happens. But empty set doesn't have any elements. And so this is true trivially, simply because there is no C in empty set. So then I get that this construction is a set of all possible sets, which is not possible. The collection of all possible sets is not a set in usual set theoretic context. But when we are limiting ourselves inside a given pose set, then it will not be the largest possible thing, but it will be the largest possible thing inside here, which is the entire set X as an element of power set. So that's how we kind of avoid this problem of this not being given defined by considering the pose set of the power set X, where the relation is given by subset inclusion. And then we can state the axioms of open set topology to say that it's a subset of power set which is closed under arbitrary joins or suprema and finite meets or infima. So the condition 1 then gets subsumed under conditions 2 and 3. Let me see if there was anything else I wanted to add to our discussion today. I think not. I think not. Well, actually, there was one thing I wanted to say, but we don't have time for that. I'm just going to say it without writing anything down. It turns out, quite magically, that any poset can be seen as a topological space. So the notion of a topological space turns out to be a generalization of a poset. And that's quite a fascinating fact, and you might want to give it a try yourself to see how you can picture that. But unfortunately, we don't have time to talk about it now. Okay, so that ends the lecture on topological spaces, where we just gave the very first introduction to the idea of an open set topology. If you have any questions, please ask them. Otherwise, we're going to stop here.
Prof, with regards to the last example that you gave, the figure 8 with the circle there, also one could give the argument that the point on the figure 8 would have, or the point where the figure 8 is actually made there would have, there's no such point that would have such a property in the circle. Hence, they are topologically different, right?
But how would you formulate the property? What is the property that point in the figure 8 has? Yeah, but intuitively, I agree. Yeah.
So an open set there. There's no such. Okay, we could consider like a points in the circle. They would have more or less the same open sets, in the sense if we consider the circles as lines of, and then their open sets would be arcs which have open endings.
Yes, and their unions. Yeah.
Yes. So in the figure 8 instance, we cannot have such yeah, we could not have such an instant, like such a set there for that particular point there.
So here I'm showing an example of an open set on the right hand side. It's the two blue areas together, seen as one set.
Yes.
So we could have an open set here. I think the way I can see that we can formalize your idea is the following. So consider this set. This will be open in here, right?
Yes.
But it's a bit more than just being open. It's something that's called connected. You can define a connected set to be a set which is not a union of two disjoint open sets. Yes. So imagine, like in the intuition of open balls, open spheres. Something like this is disconnected because it's basically union of two disjoint open sets. But I wouldn't be able to take something like this and present it as a union of two disjoint open sets. I mean, if they're disjoint, it means that they don't share a common element. But what about the boundary between? I mean, where do I make the cut, right? What about the boundary? The boundary has to be one of them, and if it's one of them, it's not open anymore. It's a very primitive way to understand the intuition behind this. So this blue set is connected here on the left side. On the right side, each of these are connected but the union is no longer connected, of course. But the feature of this connected set is that just by removing one point from it, just by subtracting one point from it, right? Subtracting this orange point, we now suddenly get 4 open sets, yes, that are disjoint from each other. Do you agree with that?
Yes.
So the 4 I mean are these 4. This 1, 2, 3, 4. Just by removing one point from a connected open set, I get 4 open sets that are disjoint. Yeah.
Yes.
Whereas here, if I take a connected set like this one and I remove only one point from it, I will only get 2 disjoint open sets. The remaining will be only 2. Yeah. I will never be able to get 4. Does that make sense?
It does.
Mm-hmm. So maybe that's a way to see, that's a way to formalize your idea that so there is some property that this point right here has, and the property is that it has a surrounding which is a connected open set, so that when you remove that point from that surrounding, you're left with 4 separate parts, whereas here no point has that kind of surrounding.
Yes, and then hence we can draw that they are not homeomorphic.
Yeah, because indeed, because if 2 spaces are homomorphic, this notion is set up in such a way that every single topological property one space has, the other one will also have. So if one space admits a point that has this interesting feature and the other space is homomorphic to it, then the image of that point under that continuous bijective homomorphism will have the same property in the other space. But since there is no such point here, that's how we conclude that there can't be a homomorphism. Yeah.
Yes, Prof.
So thank you for that remark, because it allowed us to go a bit deeper into understanding what's going on here. But I'm wondering, now if my my idea. So I mean, based on the same argument, we would then be able to argue that this space, the T junction, cannot be homomorphic to a cross, because it's the same argument. So if I remove this spot here, I will be left with 3, but here removing this spot leaves me with 4. Yeah, for some reason I'm starting to doubt myself a little bit, but I can't disprove what I said before.
But okay, with regards to also coming up with counter examples, though, Prof, we require that all in one space, for each and every point that has a certain topological property, we expect to find image of or rather another point in the space we map to that will have the same topological properties as the other ones, right? So with regards to giving counter examples, then we could argue with regards to, say, removing points, although whenever we talk about continuity and giving topological properties, we or it's emphasized that we don't tear or cut the space as such, but because what I'm trying to get is with regards to also some of the arguments that we are providing now, would that not be considering like cutting and tearing if we consider removing a certain point or the likes?
No, but of course it would be. But I'm definitely not saying that by removing this point we get a homomorphic space. I'm just describing the property of a point, right?
Oh, okay. Yes. Okay.
Yeah. In fact, if I remove a point from figure 8, if I did remove a single this point, then we will basically get a space that's homomorphic to this space. So it's basically the union of two open intervals, because I can now unfold that, right? Just get two open intervals like that.
No. Yes.
Another striking example of two spaces that are not homomorphic to each other is, of course, the surface of a sphere and the plane. And the fact that they're not homomorphic means that if I want to map Earth on a piece of paper, I will have to cut it somewhere. I cannot map Earth on a piece of paper without distorting the continuity of the surface of the Earth. Yeah, I'm now thought for a few more minutes about this, and I don't think that I said anything wrong here. I think this argument works. And to turn this into a rigorous argument, one would have to first develop this notion of a connected set in a topological space, which I already described what it is. It's just a set that can be presented as a union of two subsets, neither of which is two subsets that don't intersect each other, and at the same time, neither of them is the empty set. So this blue area here is well, actually, I could even make the argument simpler. Yeah, I think it's possible to simplify this argument to make it even more convincing, which is basically based on what I just said about the removal of the point from the figure 8. So let's take figure 8, right? And let's indeed remove the single point. When we remove the single point, we get a space that looks like this. Because that point is no longer there, there is no way to detect any close relationship between the endpoints of those loops. So we can unfold them. And we get two open intervals. So these are all open-ended points. We get two open intervals. So just by removing one point from my space, I get a space that's splits up into two open intervals. Whereas if I take a circle and I try to remove any of its points, I will just get something that's just a single open interval. Right? I will not be able to present a single open interval as two open intervals that are disjoint from each other. So, in other words, if I remove one point from a circle, I will get a connected space. But if I remove one point from figure 8, I will get a space that's no longer connected. And connectedness of the space is something that's invariant under homomorphism. And because on one side I've got disconnected thing, and the other side I've got connected thing, they couldn't have been a homomorphism. But to be able to prove everything what we just sketched here in precise mathematical terms, one has to develop some machinery for this. Defining a connected set or space is the first step, and then also dealing with the geometry of the circle and actually proving that if you do remove one point from the circle, well, first of all, we need to define topology on circle, right? We all kind of hinted what the topology would be there in terms of what the open sets would be. So there will be just unions of these open intervals lying on the circle. Remember, we are only considering the space of the circle itself, not the inside part, right? And then formalize all these ideas into rigorous proofs, and then a large part of topology deals with taking some intuitive ideas that you can feel intuitively using our ability of our mind to imagine things in space, and then formalizing them. Sometimes this process is completely non-trivial. That's one of the fascinating parts about topology, is to get formal proofs for intuition based on the imagination of the spatial imagination of our mind. Okay, any other comments or questions?
Just to repeat what you just said about the power set, and then being how that relates to a topology.
You mean here, what I was saying here?
Yes.
Rewriting axioms in terms of this power set. Is that what you wanted to?
Oh yes, not power set, power set. You said just repeat what you had said about power sets and being.
So let me phrase it as a theorem then.
Okay.
A subset tau of power set of X is an open set topology on X if and only if in the post set consisting of power set of X as the set and the subset relation as the order relation of the partially ordered set. This tau is closed under finite meets or infima. Meet is another term from infimum. I think Dr. Gosh explained that. Under finite meets and arbitrary joins, or in other words, arbitrary suprema. So basically, we have two axioms: closure under finite meets and closure under arbitrary joins, instead of having three. So the remark here that kind of leads to this theorem is that for empty set, the infimum of meet of the empty set is the bottom element of your post set, and the sorry, not the bottom element, the top element of your post set, and the join of the empty set is the bottom element. So in our case, top element being X and bottom element being empty set. So to say that X and the empty set are both open, in other words, elements of tau, is the same as to say that tau is closed under empty meet and empty join. Okay, so that takes care of the empty case, kind of covering the first axiom. And of course, once the empty case is out of the way, then to say that tau is closed under binary meets, but meets in that post set, I mean, in this post set, meets are just intersections, say, and for binary, and joins are just unions for arbitrary. So to say that it's closed under binary meets, it's the same as to say closed under meets of arbitrary number, as long as that number is finite, because we can form a meet of n many objects by meeting the first two, then meeting that with third, sorry, and then meeting that with the fourth, and so on. So this becomes equivalent to being closed under finite meets, where finite includes the empty case as well, but the empty case is covered by this, as we discussed. And then this becomes closure under arbitrary joints, because joints are the same as unions. Does that, are you happy with that?
Yes, very much.
Right.